Hello and a very happy Navratri to all our viewers. I'm Varun Krishnan and I'm going to be taking forward our Navratri Shiksha Utsav series with this small video on a concept which is very, very fundamental to geometry, in which I'm going to be looking at Euler's Polyhedra theorem, which is a very, very basic theorem in geometry, considered to be one of the most famous and most important equations ever in geometry. And I'm going to be looking at how we can apply Euler's Polyhedra theorem, which is a theorem made for 3D geometry, and how can we translate it into a theorem which can be used in 2D geometry questions. So first, to begin with, let me introduce you to what is meant by, or what is the Euler's theorem on Polyhedra. So Leonhard Euler, one of the most prolific mathematicians of the modern age in the 18th century, had written down this particular formula for Polyhedra in a letter that he sent to another great mathematician, Christian Goldbach. So this particular equation that he came up with says that for any polyhedron, so polyhedron are any three-dimensional shapes which are completely enclosed using planes, be it a cube, a cuboid, a hexagonal prism, an octagonal prism, or a Buckminster Fullerene. All of the closed polyhedrons in the world will follow this equation that V minus E plus F is equal to 2. This is a very, very basic equation where V stands for number of vertices, E stands for number of edges, and F stands for number of faces. And it has always puzzled mathematicians all over the world. That geometry as a topic was extensively studied in the before Christ era, in the BCEs. And by 300 BC itself, Euclid has written his all-encompassing work on planar and three-dimensional geometry. Yet it took till the 18th century, till the 1700s, for someone to discover the fact that the vertices and the edges and the faces of any polyhedra in the world will actually follow this rule that V minus E plus F is equal to 2. Nowadays, we find the application of this theorem in several different architectural applications. Also, anywhere 3D models need to be created for mathematical and physical and engineering simulations. This equation lies at the very basis of creating any 3D models. So this is a very, very simple equation to get a sense of understanding of that for in a closed polyhedron, the number of vertices minus the number of edges plus the number of faces will always be equal to 2. This was first written by Leonhard Euler. So this is for three-dimensional objects. But what if we want to come up with a similar kind of a theorem for planar shapes and for polygons instead of polyhedra? Then how will that equation look like? That is what we will try to derive in this particular video. So for that, let me translate V, E, and F into, say, 2D components. And the 2D analogous components will be nodes, which are going to be the ending and the starting points of straight lines. S is going to be sides, which are going to be, of course, sides of the polygons, which have a starting point and an ending point. And A, which is denoted as every isolated area enclosed. So how many areas are getting enclosed by the sides when we are creating the polygons? Let's see if we can form a relation between N, S, and A. So to derive this, let's start with a very, very trivial case where I say I have only one node. So when I have only one node, of course, there are going to be no sides, because for having a side, I need to connect two nodes. So I've got only one single node. So no sides and, of course, no areas getting enclosed. So which means I can say node is 1, number of sides is 0, and the number of areas which are getting enclosed is also 0. Now, if I include a side, if I draw a side from that node, of course, I will form one more node at the end of that side. So now what happens is that I've got two nodes, one side, and still 0 areas being enclosed. If I add one more side, then again, that will lead to one more node. So which means now I've got 3 nodes, 2 sides, and still 0 areas. So if you see, what is happening is that as I keep on adding more and more sides, if I add one more side, I will get one more node, one more side is still 0 area. So what this actually tells us and what this actually shows us is that as I keep on adding one more side, the number of nodes, of course, is going to increase by 1. So which means we can clearly see that the difference between the number of nodes and the number of sides is always remaining constant at 1. But what happens when I join two pre-existing nodes like this? So when I join two pre-existing nodes, what is happening is that I'm getting one extra side, but my number of nodes is remaining constant in the figure. So now the difference between nodes and sides is no longer 1. But what is happening when I join one node with another pre-existing node is that I will end up creating one enclosed area. So this is an isolated enclosed area. So what is happening is that if I increase the number of sides while keeping the number of nodes constant, the number of areas is going to increase by 1. And this is always going to happen, that when I introduce a new side, either I will increase the number of nodes or I will increase the number of areas. So what this tells us clearly is that the number of nodes plus the number of areas will always be 1 greater than the number of sides. So the two-dimensional counterpart of Euler's polyhedra theorem can be written as n minus s plus a will always be equal to 1. So this is a fundamental geometric equation or theorem that we can create for polygons for sure, and this will hold for every single polygon anytime I'm forming a polygon using nodes, sides, and enclosed areas. That number of nodes minus the number of sides plus the number of isolated areas enclosed will always be equal to 1. Now, shrewd students here will actually observe that so far we have only been drawing sides. We have only been joining nodes in such a way that no two sides are intersecting each other. So then what happens if I join two nodes? Maybe say if I join this node and this node, where the side which is joining these two nodes is going to intersect an existing side. Is that going to be a case where this equation is going to get disproved, or this equation is not going to hold true? Let's understand whether it does or not. So for that, again, let me start with this case where I've got 5 nodes, 6 sides, and 2 areas. So when I join these two nodes, then what is happening is clearly I can see that the number of nodes is remaining constant at 5. The number of sides is increasing by 1, it's becoming 7. And the number of areas is increasing by 2, because now I've got 1, 2, 3, 4 separate enclosed areas. So I've got 4 here. So which means now it might seem that n minus s plus a is no longer equal to 1. Rather, n minus s plus a is becoming equal to 2. So then you can say that then n minus s plus a does not hold true for this case, and that's why we cannot call it a theorem. But I will disagree with that, because that still holds as a fundamental theorem that n minus s plus a will still be equal to 1. Because what we have to understand is that when we are having two sides intersecting each other, we will have another new node at the point of intersection. So if I consider the point of intersection as a new node, then what is happening is that the number of nodes now becomes 6. But the number of sides is also increasing, because if you count the number of sides, now I have got 1 side, 2 side, 3, 4, 5, 6, 7, 8, 9. So I have 9 sides now, and still I have got 4 enclosed areas, 4 isolated enclosed areas. So which means that now if I do 6 minus 9 plus 4, this still becomes equal to 1, which means that the theorem n minus s plus a equal to 1 will always hold true. This is the two-dimensional version of Leonhard Euler's polyhedra theorem, and this will hold true any time that I'm joining a set number of nodes with each other to form enclosed areas. So this equation can be useful in very select geometry questions, in fact, in certain permutations, combinations, and probability questions as well. I will not get into solving of questions in this video, but I hope everyone is absolutely clear with how this theorem and why this theorem always holds true. So that is all that I wanted to communicate through this short video. Hope you found this fact to be extremely interesting, and hope this is helpful in some form or the other. So thank you, everyone, and wishing you all once again a very happy Navratri. Take care.